Hello again. On to the second module of sixth chapter, which is all about the elastic and plastic behavior and their graphs. So the first thing you need to understand is these terms, which is elastic deformation, plastic deformation, and elastic limit. So what I'm going to do here now is just draw a graph for you, a full graph of what happens when you extend an object. So the first thing that you probably know is it goes straight. This is fx graph, by the way, right? So it just goes straight up, but then it goes like this, and then it goes haywire, right? So there are some key points in this graph, which is the first one that we discussed in the previous video, which is limit of proportionality, and this one, which is elastic limit. So what elastic limit means is how much an object can be deformed and returned to its original position, right? So for example, if you take a spring and you extend it so much that it breaks, right? So it has gone past the elastic limit, but if it doesn't break, it has not gone past the elastic limit. So that's what elastic limit tells us, right? That whether or not the object is going to go back to its original place. So if you apply a force, for example, this amount of force, the object will break down. But if you apply this amount of force, the object will not break down, right? So this is the simple concept of elastic limit. Now, what is elastic deformation and plastic deformation? So this region here, this is elastic deformation, right? Elastic deformation. And elastic deformation just basically refers to deformation that returns the object back to its original position. And the plastic is the opposite, which means that plastic deformation means that object will not return to its original position. Now moving on to our another fx graph, right? Now understand that area under the forced extension graph represents the work done. For example, this is the force extension graph and the limit of proportionality hasn't been reached. And this is the force that is applied, and this is the extension. Now, you know that if you find the area under this, you are essentially just multiplying f and x, right? So the f is a force, and x, what is s? X is basically a length or a distance, right? So this becomes equal to work done, f into d, right? This just becomes f into d, or let me just write x here. So this just area under the force extension graph is work done on the object, right? So the work done is basically when you do work on a spring by compressing it or extending it, what you're doing is just giving it more elastic potential energy, right? You're just giving it potential energy. So this work is basically energy converted by the force to potential energy in the spring. When you remove the force, the object bounces back to its original shape, right? So that is the work done. Determine that elastic potential energy of a material deformed within its limit of proportionality from the area, right? So this is basically the concept of elastic potential energy. Now, another thing you need to understand is about this graph is the work done is not force into distance here, but the shape of the triangle, which is 1/2 f into x, right? Because we need to account for the shape of the graph. So 1/2 f into x, and that is the elastic energy / work done on the spring, right? Elastic energy gained by the spring or work done by the spring. And this can be written in a few forms, which is 1/2 f into x, right? Or 1 by 2 kx square, right? And this is derived from the formula. Look here, f is equal to kx, right? So this is just basically f is equal to kx, putting it here. So this becomes f 1 by 2 kx square. So these are the formulas of elastic potential energies right here. And we'll be calculating all of this and going into the nuances of this in the topical sessions. As for now, just memorize all this. You should just know what elastic limit and what is the area under this graph and whatnot, so you won't be lost behind in the past paper sessions. So for now, goodbye, and I'll see you guys in the next video.